Hello everyone, in this video we'll discuss about free multi-degree of freedom vibration system. Now, every real life system, it has the continuous or distributed parameter system. That means it may have infinitely many degrees of freedom. Therefore, it is quite important to understand and study how a system with n number of degrees of freedom behave or respond when force is being applied to it, right? So it doesn't matter that whatever system we are studying and what number of degrees of freedom we have. The simple steps that are to be followed is to consider the system in displaced configuration, to draw the free body diagrams and apply the Newton's second law to write the equations of motion. So once the equations are there, we can easily solve it and get the resultant or whatever analysis we want to do, that can be done. Now we have already studied for the body with single one dimension or 1 degree of freedom, that let's assume that if there is a mass, right, and that is attached to a spring, right, and let this mass be m with some spring stiffness s, and if some force is being applied in this direction. So the equation of motion that we used to get was, if let's say this is the equation where damper is also added, so the equation we used to get was mx double dot, which is the acceleration of body in this direction, because this the direction of force, this is the direction of the displacement, velocity and acceleration. So the equation that we get is mx double dot plus cx dot if we take damper into account. So this gives the damping coefficient, which is c, right, and plus sx, which is the spring stiffness into the displacement. And if the force applied is a linear static force, so the equation will be F naught. If we are applying a dynamic force, let's say some harmonic force, so equation will come out to be F naught cos omega t. So for this equation, if we solve, we say that displacement is what? Amplitude, which is x cos omega t minus phi. So we take phi, which is the phase angle. If we say that the displacement, now see, whatever is the frequency of force, same is the frequency of displacement. But there is a possibility that there may be some phase lag. So if this is showing, let's assume that this is a curve which shows force. So there is a possibility that displacement might be something like this. So this gap shows the phase lag, right? So the phase lag, it may vary from 0 to pi. So this is the condition which may happen or which may not happen, right? So let's take a 2 degree of freedom system, which is nothing but the extension of a system with 1 degree of freedom. So here we have two masses, let's say M1, M2, and two springs with spring stiffness K1 and K2, right? And the mass M1 is having displacement in this direction and M2 is having displacement in this direction x2. So if we draw the free body diagram, so how they will look like M1, this mass M1. So when force on this M1 is applied in this direction, so the spring force, it will act in opposite direction, which is K1 x1. But also this mass is attached to another spring of spring stiffness K2. And what is the displacement of this K2? It will be the relative displacement cost because of M2 and M1. So it will be K2 x2 minus x1. So the equation of motion that we'll get is this, which is m1 x1 double dot plus k1 x1 minus k2, and the relative displacement, which is x2 minus x1, and this is equal to the force applied, which is F, let's say F1t, because this force is applied on the mass 1. So if this force is a static force, the equation will be something like F1t. And if this force is a dynamic force or some harmonic function we take for force, so it becomes F naught cos omega t. Now we draw the free body diagram for mass 2. So it will be m2 x2 double dot. That means the acceleration is in this direction is equal to minus of, basically the equation is like negative of K2 into X2 minus X1. So if we take it on the side of this force, so the equation looks like this. So here we have two equations, and if we try to write these two equations in the form of matrix, we get this equation, right? So which is M1 and M2, these are placed, right? And so basically the equation is M into X double dot. So this is X1 double dot, X2 double dot plus the stiffness. So for X1 and X2 we are writing the components. So for X1 it is, so in this equation if we take the components of X1, it comes out to be K1 and plus K2. So K1 plus K2, and for X2 it is minus K2 in this equation, in the first equation. Then in the second equation, the factor for X2 is K2, so this is K2, and for X1 it is minus K2, so this is this factor, which is equal to F1T and 0, right? So this is how we can write the equation in the matrix form. Now, if we write the general form of solution for this equation, so it will have two natural frequencies and two modes of oscillation. So this is how we can write the equation where the displacements x1, x2 are there, right? And this component is denoting the free response and this component is denoting the forced response, right? So this is the component because of the forced vibration of the system, and this is because of the free response of the system. And in the free response equation we see that C1 and C2, these are the vectors which describe the modes for free response. And if we see omega 1 and omega 2, these are the two natural frequencies of the oscillation, and they are these constants A1, A2, phi1, phi2. So A1, A2 are the constants and phi1, phi2 are showing the phase difference which depends upon the initial condition of the system. But here we are concerned only about this forced response. So we will not take into consideration the free response, we'll only talk about the forced response. So the equation, it looks like this, where x1, x2 is equal to x1, which is the amplitude, x2 and cos omega t. And we say that there is the phase change, the possibility is of 0 to pi. So let's assume that the phase change is 0. So the equation becomes cos omega t. So instead of taking cos omega t minus pi, we are just taking cos omega t and assuming that the phase change is 0 or pi, right? So the equation looks like this. So if we take, and now we know that if x is x cos omega t, the velocity is minus x omega sine omega t, and acceleration is minus x omega square cos omega t. Now we again go back to our matrix condition. This factor is the acceleration factor. That means we are concerned with this form of equation. So if we are taking the angle omega as let's say 0, so the equation becomes minus x omega square. So if we take x now, for m1 x is x1 and for m2 x, this amplitude is x2, right? So this x1 x2 can be replaced with x1 and x2. Now these factors of k remain the same, and what this acceleration, it is replaced by what? Minus omega square, because we are taking x1 x2 common for both the terms of mass or the inertia body and the spring. So this acceleration factor, which is x double dot, is replaced by minus omega square. So this will be the equation, and we are assuming that whatever the force is being applied is on m1, which is F naught, and no force is applied on mass m2, so this becomes 0. Now if the equation would have been that some force is applied on this m2 also, so here we might have written F2t, right? So if you want to find the values of x1 and x2, it becomes this factor of the spring stiffness, the inverse of this, and F naught and 0. And because this is addition, right, so we can add these terms of minus. So this is basically m1 minus m1 omega square, minus of m1 omega square. So we can add it up, right, on this position, which is a11. So this is 2 by 2 matrix, this is, right, and minus k2 remains same, and this a to 2. So here also we have got a component which is minus m2 omega square. So this is also added to the equation, right? Now if we want, if we say that this is some matrix, so it can be written in this form. These are showing the rows and columns. So a11, a12, a21, a22. And because this is showing the inverse, if I want to find the inverse of this, what it will be? So this is the adjugate and this is the determinant, right? So we can write the equation in this form if we want to find for x1 and x2. So the determinant of the whole this matrix and the adjugate of this matrix, which is given by okay, this part, right? So we can write it this way into f naught into 0. Now whatever are the conditions given in any numerical which displays the values, you can solve it and you can easily find the value of x1 and x2, or maybe whatever is unknown in the equation. Now we can take the example of 5 masses. Now because the question talks about infinite degrees of freedom, so let's extend the equation or extend the question, and let's assume there are 5 masses which are connected to 6 springs and which are attached to these free ends, right? So the displacement of mass m1 is x1 in this direction, same is the direction of its velocity and acceleration. So same is the direction of displacement for all the masses, right? So if we draw the free body diagram of mass m1, so the force applied is F1T. Now, if we are assuming the static force is there, it will be F1 or F0, whatever is the value. And if we assume some dynamic forces there, then we may use any harmonic function, maybe sine or cos function, right? Now, because this mass is attached to two springs, one is S1, so the displacement, the spring force will be in this direction, which is S1 x1, and the second spring that it is attached to is this spring. So it will be the force because of this spring S2 will be S2 into x1 minus x2, because it is talking about the relative displacement. And the direction of this mass into acceleration will be in the same direction as the displacement. So it becomes m1 x1 double dot. Now we try to plot a free body diagram for mass m2. So this mass m2, it is again attached to two springs, 2 and 3. So it will have two spring forces along with the relative displacement. So this is s2 into x2 minus x1, and this is s3 into x2 minus x3. And if some external force, if let's say is applied on this body, it is F2 into 2, and the direction of M2 into X double dot is same as the direction of displacement and velocity of the system. So we write the equations of motion on the basis of these free body diagrams. The equations will look like this. So this is S2 plus S3, which is M1 X1 double dot plus okay, so what we have done, we have just opened the bracket and we have placed all the components of x1 together and for x2 on one side. So it becomes s1 plus s2 into x1 minus s2 into x2. Similarly, we can do it for mass 2, and similarly you can do it for mass 3, 4 and 5. Now, just don't get confused. In the earlier part, I was using K as the spring stiffness. Here, I'm using S as the spring stiffness. It is not going to change the equation. The equation remains the same. I'm just telling you in both the ways because at various sources, you'll find that somewhere spring stiffness is given as S and somewhere it is given as K. Both are correct, right? So if we write these equations in the form of the matrix form, we'll write in this way, which is, now you see this is how we are writing the masses. So if there are 5 masses, you get 5 into 5 matrix, right? If there are 6 masses, you get 6 into 6 matrices. So this is how we decide the size of the matrix that we write. So it is mass into acceleration. So it is x1 double dot, x2 double dot, x3 double dot, x4 and x5 plus. So plus, what is it? It is the spring stiffness, and for the displacements x1, x2, x3, x4 and x5. Now for x1, it is s1 plus s2, right? And in the component of x1 here, right, this which is minus s2. So minus s2. Similarly, we can write for x2, that means the displacement of spring 2, which is 2 has got this component which is minus s2 here, and s2 plus s3. So these are the components, and if you write the next equation for the third mass, we'll get another component which is minus s3. So similarly, we can write all the spring stiffnesses factors by writing the free body diagrams and the equations of motion for all the masses given, which is equal to what? The force applied, which is F1T, F2T, F3T, F4 and F5, because force is the function of time. So if we write the generalized equation, we can write it this way: mass into displacement, mass into acceleration plus spring stiffness into displacement. It is giving what? The value of force. So now there may be question giving n number of factors. Let's say the forces, externally applied forces, if let's say are equal to 0, and let's say the displacement is a function, is a harmonic function which is x naught into sine omega t. So the way we did for 2 degree of freedom, similarly we can place the equations, right? So if this is x naught sine omega t, so x double dot will be in terms of minus omega square. So you can just replace the values of this x double dot can be replaced with minus omega square, and this is how we can solve the equation. Now, if we find the eigenvalues of this system, right? So the eigenvalues of the system, they will give the natural frequencies of the system. And if we find the eigenvectors corresponding to individual eigenvalues, they give the mode shapes of the system.